Welcome students to the fourth lecture on fuzzy sets, arithmetic and logic. In the last lecture, we discussed two important topics, namely alpha cuts and convex fuzzy sets. For a given fuzzy set A, its alpha cut is the crisp set denoted as alpha A like this, which is the set of all the points x such that membership of x in A is greater than equal to alpha for all alpha belonging to 0, 1. And strong alpha cut is defined as denoted as alpha plus of A, which is the set of all x such that mu A x is greater than alpha. So, the difference is that in this case the inequality is a strict inequality. In the definition of alpha cut, we have used greater than equal to. And what is the convex fuzzy set? A fuzzy set A is said to be convex if for all alpha corresponding alpha cuts are convex sets. And a fuzzy set A is said to be convex if and only if for all points x lying on the line joining 2 points x 1 and x 2 belonging to A, the mu A of x is greater than equal to minimum of mu A of x 1 and mu A of x 2. I have proved the theorem. Now, let me show you with a diagram. Suppose this is a convex fuzzy set. Now, consider the points x 1 and x 2. Now, if we look at any point x on the line joining x 1 and x 2, and we look at its membership value to x, you find that the membership value is more than the minimum of the membership value of x 1 and membership value of x 2. Since in this case membership of x 1 is smaller than membership of x 2, we will look at all the points and we can easily see that their membership values are more than the membership of x 1 to a, which is equal to say this point, let us call it say beta. So, for all these intermediate points the membership value is greater than beta. This however, is not true if the fuzzy set is not convex. For illustration, consider a fuzzy set with this type of membership. Consider this to be x 1 and this to be x 2. Then we can see that for all the points we have the membership values actually bigger than the smaller of mu a x 1 and mu a x 2. Therefore, it can hold for some of the x 1 x 2 lying on the line, but suppose I consider this x 1 and this x 2. So, these are the set of points lying on the line joining x 1 and x 2, and we can see that there are intermediate points whose membership is not greater than equal to the minimum of mu a x 1 and mu a x 2. In fact, you can see that it is smaller than that. This happens because this is not a convex fuzzy set. With that background, let us now study some properties of alpha cut. So, let A and B be two fuzzy sets defined on universe U. Then property 1, for all alpha alpha plus A is contained in alpha A. This is obvious. Why? Because if x belongs to alpha plus of A, then mu A of x is strictly greater than alpha. Therefore, implies mu A of x is greater than equal to alpha, implies x belongs to alpha A. But this is not true otherwise, because there may be x belonging to U such that mu A x is equal to alpha. Therefore, this x belongs to alpha cut of A, but does not belong to alpha plus of A. Property 2, if alpha is less than beta, then beta cut of A is contained in alpha cut of A. This is obvious. Since beta is greater than alpha, if x belongs to beta cut of A, mu A of x is greater than equal to beta, which is greater than alpha. Therefore, x belongs to alpha cut of A. Alpha cut of A intersection B is equal to alpha cut of A intersected with alpha cut of B, and alpha cut of A union B is equal to alpha cut of A union alpha cut of B. So, let me call them A and B. So, let me prove them. So, proof. Let me first prove the A part. Suppose x belongs to alpha cut of A intersection B, implies minimum of mu A of x and mu B of x is greater than equal to alpha, implies both mu A of x and mu B of x is greater than equal to alpha, implies x belongs to alpha cut of A and x belongs to alpha cut of B. Since x belongs to both the sets, implies x belongs to alpha cut of A intersection alpha cut of B. Conversely, suppose x belongs to alpha cut of A intersected with alpha cut of B, implies x belongs to both alpha cut of A and alpha cut of B, implies mu A of x is greater than equal to alpha and mu B of x is greater than equal to alpha, implies minimum of mu A of x and mu B of x is greater than equal to alpha, implies x belongs to alpha cut of A intersection B. Therefore, alpha cut of A intersection B is equal to alpha cut of A intersection alpha cut of B. Now, proof of B, that is alpha cut of A union B is equal to alpha cut of A union alpha cut of B, can be proved in a similar way. For example, suppose x belongs to alpha cut of A union B implies maximum of mu A of x and mu B of x is greater than equal to alpha, implies x belongs to alpha cut of A or x belongs to alpha cut of B implies x belongs to alpha cut of A union alpha cut of B. Conversely, suppose x belongs to alpha cut of A union alpha cut of B implies either mu A x is greater than equal to alpha or mu B x is greater than equal to alpha. Therefore, x belongs to at least one of alpha cut of A or alpha cut of B implies x belongs to alpha cut of A union B, since maximum of mu A x and mu B x is greater than equal to alpha. Very similar properties can be proved with respect to alpha plus cuts also. That is, A alpha plus of A intersection B is equal to alpha plus of A intersected with alpha plus of B, and alpha plus of A union B is equal to alpha plus of A union alpha plus of B. Prove yourself. Since the proof is in a very similar line, I want you to prove them yourself. Another property is alpha cut of A complement is equal to 1 minus alpha plus cut of A complement. You have to understand that this is fuzzy complement. A is a fuzzy set, I am looking at its fuzzy complement, and then I am looking at alpha cut of that. But this is a crisp set complement, one minus alpha plus cut of A is a crisp set, and I am looking at its complementation. So, you have to remember this. Let me give the proof. suppose x belongs to alpha cut of a complement, that is mu a complement of x is greater than equal to alpha. Since mu of a complement of x is equal to 1 minus mu a of x, therefore, 1 minus mu a of x is greater than equal to alpha, implies mu a x is less than equal to 1 minus alpha, implies x does not belong to 1 minus alpha cut of a, implies x belongs to this is alpha plus. Therefore, since mu a x is less than equal to 1 minus alpha, x does not belong to 1 minus alpha plus of a, because here we look at strict inequality, implies x belongs to 1 minus alpha plus of a complement. Conversely, suppose x belongs to 1 minus alpha plus of a complement, implies x does not belong to 1 minus alpha plus of a, implies membership of a to x is less than equal to 1 minus alpha, implies 1 minus mu a of x is greater than equal to alpha, implies mu a complement of x is greater than equal to alpha, implies x belongs to alpha cut of a complement. These are some interesting properties with respect to alpha cut. In some of my subsequent lectures, I shall deal with these properties in a slightly more generalized way. In the remaining part of this lecture, I shall start studying operations of fuzzy set. We have already seen that the three main operations on sets are complementation, intersection, and union. We have already seen some methods for doing it. For example, complementation we have done 1 minus mu a of x, intersection we have done using minimum of mu of x and mu b of x and union we have done using maximum of mu a of x and mu b of x. However, why should these be the only way of operating on fuzzy sets? We have seen different shapes for membership functions. And we have discussed, depending upon the application, one may model membership functions in different ways. In fact, in one of my earlier lectures, we have seen different types of membership functions. Then, depending upon the applications, one may model the above set operations or say fuzzy set operations in different ways. So, this led to more generalization of these set operations. In particular, let us first consider complementation. So, how to model mu a complement of x from mu a x. Actually, we will see that sometimes complementation may have different interpretations. Example, what is the complement set of say tall? If I ask you the question, I am sure most general answer will be short. Then what is the complement class complement set for very tall, complement of very tall is surely not very short. So, common intuition sometimes fails. Hence, when generalizing complementation we need to focus on properties that the complementation function should have. Okay. So, in general, a complementation function may be denoted as C, which is defined from the set 0 to 1, the closed interval, to 0 to 1. What does it mean? It means that if mu a x is equal to a belonging to 0 1, then mu a complement of x is equal to C of a, which again lies interval 0 to 1. Thus, given mu a of x, we can compute mu a complement of x by applying function C. Question is, what are the properties of such a function C? Axiom 1, C of 0 is equal to 1 and C of 1 is equal to 0. So, these are called boundary conditions. What does it mean? It means that if membership of x to a fuzzy set A is 0, then the membership of x to its complement set is 1. This comes naturally from the concept of crisp set. If membership is 0, that means x does not belong to the set, therefore, x belongs to the complement. In a similar way, if membership of x in A is 1, that means if x is a member of the set A, its membership to the complement set is 0. If A is less than equal to B, then C of A is greater than equal to C of B. This is called monotonicity. That means, if membership of x in A is less than equal to membership of y in A, then membership of x in A complement has to be greater than equal to membership of y in A complement, which is understandable. These two are must, essential properties. Two more desirable properties are C is continuous. This is required to ascertain that a small change in membership should not lead to big jump in the complement, in the membership of the complements set. And there is a fourth property, which is C is involutive. That is, C of A is equal to A. That is, complement of A is A. However, all these four properties are not independent. Let me give you a few results. If C is involutive, then C is bijective. That is 1 to 1 and on to. Proof. Since C is defined on 0 1, for all A we can compute C of A when A belongs to 0 1. Let us show that C is onto. That is, given any B belonging to 0 1, there exists A belonging to 0 1 such that C of A is equal to B. So, since C is involutive, C of B is equal to B, and by above observation, and we know that C of B belongs to 0 1. Therefore, given B, we get C of B such that C of B is equal to B, implies C is onto. Now, suppose there exist A 1 and A 2 such that C of A 1 is equal to C of A 2. Therefore, C of A 1 is equal to C of A 2, and by involution implies A 1 is equal to A 2. Hence, C is bijective, that is, if A is not equal to B, then C of A is not equal to C of B. If C is monotonic and C is involutive, then C of 0 is equal to 1 and C of 1 is equal to 0. Proof: since C is a mapping from 0 1 to 0 1, C of 0 is less than equal to 1 and C of 1 is greater than equal to 0. Since C of 0 is less than equal to 1, by monotonicity C of 0 is greater than equal to C of 1, implies 0 greater than equal to C of 1, implies C of 1 is equal to 0. Similarly, since C of 1 is greater than equal to 0, C of 1 is less than equal to C of 0, implies 1 less than equal to C of 0. Therefore, C of 0 is equal to 1. Another interesting result is, if C is bijective, then it is continuous. Let me give you a proof. Suppose C is not continuous and let A be a point of discontinuity. Therefore, since C is monotonically decreasing, we may have the following. At 0, it is 1, at 1, it is 0, and suppose A is a point of discontinuity, therefore, we shall get such a type of picture if A is a point of discontinuity. Therefore, if we take limit x goes to A minus of C of x, that means we are moving towards A from the left side. Therefore, the limit is going to be this value, let me call it B 0, and if we take limit x goes to A plus, that means we are moving towards A from this side, then the limit will come to this point. Let us call it B 1. Therefore, for any y belonging to B 0 to B 1, this open interval B 0 and B 1, there does not exist any A naught such that C of A naught is equal to y, because for no values of A naught in the interval 0 to 1, we can achieve an intermediate point of B 0 and B 1 to be the value of the complement. This contradicts the bijective property of C. Therefore, C is continuous. Examples: let C of A is equal to 1 if A less than equal to T 0, otherwise T belongs to 0 1. Therefore, if this is T, we are looking at a function such that for these values it is 1 and for these values it is 0. So, it is one of the simplest kind of complementation. Another example: C of A is equal to 1 minus A upon 1 plus A. Therefore, 1 C 0 is equal to 1 minus 0 upon 1 plus 0 is equal to 1. C of 1 is equal to 1 minus 1 upon 2 is equal to 0. So, this is the property 1. If A less than B, then C of A is equal to 1 minus A upon 1 plus A, C of B is equal to 1 minus B upon 1 plus B. As A less than B, 1 minus A is greater than 1 minus B and 1 plus B is greater than 1 plus A. Therefore, 1 minus A into 1 plus B is greater than 1 minus B into 1 plus A, or 1 minus A upon 1 plus A is greater than 1 minus B upon 1 plus B. This is axiom 2. Axiom 3, obviously it is continuous. Axiom 4, C of A is equal to 1 minus C of A 1 plus C of A is equal to 1 minus A upon 1 plus A, 1 plus 1 minus A upon 1 plus A is equal to 1 plus A minus 1 plus A upon 1 plus A divided by 1 plus A plus 1 minus A upon 1 plus A is equal to 2A upon 2 is equal to A. Therefore, it follows involution also. In the tutorials, I will give you many different problems involving different complementation functions. With that, I stop here today. In the next class, I shall investigate complementation slightly deeper, and also I look at generalizations of fuzzy union and fuzzy intersections. Thank you.